Hi everyone, welcome back. Today we're going to look at how to use Laplace transforms in order to solve a differential equation. However, in today's example, we're going to be using it to solve a first order differential equation. So let's have a look. So here's the example we've got. You'll see we have first order differential equation. We know that it's first order because the derivative, the highest derivative in the equation is a first derivative. Your dependent variable is I and your independent variable is t. So now, if you were using a method for first order differential equations, you'll see that this one is in fact a linear differential equation. So you would use the linear method of solving it. But today I want to show you that you can in fact use the Laplace transform in order to solve it as well. So let's begin. So what we want to do is you will see that this equation is in the time domain, right? So your independent variable is t. So what we do is we take the Laplace transform of both sides of the equation, right? And we can write that as the transform of di dt plus 4 times the transform of I and the transform of 1. Okay, so if we look at the transform of the first derivative, we recall that our formula looks something like this, right? The Laplace transform of the first derivative of a function is equal to this expression here, right? Now, just a bit of a side note on the notation that you use here. You will see that in different books they use different types of notation, right? You can use or choose whichever one feels more comfortable to you, as long as you're consistent. Okay, so what I like to do, particularly when I've got a dependent variable like here, which is not y and it's not f, right? It's I. So if I look at this formula here, what I like to do is where you've got the transform, because here f of s is your transform. That's the Laplace transform. The letter in front of that s, I like to make my dependent variable. So in this case here, if I find the transform of the first derivative, then it would be s I of s minus I at 0. I like to write it like that, because then also I can see what my initial condition is, because you see that matches with the initial condition that is given here, right? And remember that I at 0 equals 2 translates to when time or t is equal to 0, then your function I is going to be equal to 2. Okay, so that means that this expression here is the Laplace transform of my first derivative. Then my second term, because this is the Laplace transform of I can write as 4is, right? And the transform of 1 is going to be 1 over s. Okay, so now that we've got this, we can now apply our initial condition. So we've got s like that, and this is going to be 2. 2 plus 4 is equals 1 over s. Okay, then we want to put all the terms with the Laplace transform on our left-hand side. So we've got s, 4 and that's going to be 1 over s plus 2. And if we factorize, we have s plus 4, 1 over s plus 2. Okay, so there we go, right? And if we then make is the subject of the formula, we'll have 1 over s plus 4, 2 over s plus 4. Okay, so now you see your transform has two terms in it, right? At this stage, you can then apply the inverse Laplace transform. Well, that's what you want to do, right? Apply the inverse Laplace transform, so you get I of t at the end, which is your solution to the differential equation. So when you look at the Laplace transform that you've got, you see you've got two terms. The second term here is already in a form that you can find on your table, right? But now there are different ways to do this, right? You can do it that way and then only apply partial fractions to the first term here, because you see your denominator is not in a form that's on the table and you've got factors. But you can change this by using partial fractions. You can do that, or what you can do also is you can make this one term and do partial fractions. It's entirely up to you. The form of your final answer, you'd be able to simplify it to the same thing. Okay, so it's entirely up to you. I personally always like to work with just one term, right? But you don't have to, as long as you keep track of where your terms are and what you are working with. Okay, so I am going to make this one term. So that means that's 1 plus 2s. Okay? So then it means that this expression here can be changed using partial fractions. So we've got a over s, b over s plus 4. Okay? Then if we solve this, we know that 1 plus 2s must be equal to a times s plus 4 plus bs. And then if I let s equals to 0, I get 1 equals, this one is going to be 0, so I've got 4a, which means a is going to be a quarter. Okay? Then, let's just move this up a bit. Here we go. Then I can say, let s equals to minus 4. So I get 1 plus 2 times minus 4. Sorry, that must be an equals to minus 4b. So then I get, what's that? 1 minus 8 minus 4b, which means that's minus 7. So b is going to be 7 over 4. Okay? Which means we now have a and we've got b, which means that our transform is going to be a quarter, whoops, not a half, a quarter, times 1 over s plus, what's this one, 7 over 4. 7 over 4 times 1 over s plus 4. Okay? So then, if we go to our table of Laplace transforms, let's see what we have. Our first term, you'll see, just get this a bit closer to you, is a times 1 over s was a quarter times 1 over s, which means we are looking at the first one, right? So it's going to go to a constant. So that is just going to be, we have I of t is going to be a quarter, right? Plus 7 over 4. This one is going to be number 7 on our table over here. It's number 7 on our table. So it's going to be e to the minus 4t, right? And that is the solution to our differential equation. Now you'll find if you use the linear method in order to solve, it's going to work out to the same thing. You would then have to just find your general solution first and then substitute in your initial condition in order to find your particular solution. Well, I hope that video was helpful. I'll see you in the next one. Bye.